Welcome to our lesson on estimating a population proportion. So far in statistics, we've just used descriptive statistics, means, medians, modes, standard deviations, things like that, graphs, tables, to basically describe or summarize our data. Then we moved on and we introduced the idea of z-scores and critical values, and we were able to calculate kind of these critical values or these cutoffs that gave us a certain percentage, right? So z of 0.025 gave us 2.5% of our data to one side or the other of that critical score. Well, now that we have those two concepts in our tool belt, the next step is to move on to inferential statistics. And inferential statistics are really the backbones of statistics. It's really the reason why we study statistics is so that we can do these two things. And one is to be able to make some sort of estimate about a population parameter. So to be able to make a claim about what we think the mean of a population is, or what the standard deviation of a population is, or in the case of this video, what the proportion of a population is. So we'll start off with those. We'll be able to estimate those, build confidence intervals around them, and then later on we'll move on to the second kind of cornerstone of inferential statistics, which is the hypothesis test. And that's really the biggie. That's the one that you'll see in journals and in newspapers and reported all the time. So being able to make these kind of scientific claims or educated guesses and then test them statistically. Those are the two big things. So let's start off with our estimates of a population proportion. And a proportion is just a percentage of things, right? So we normally do this type of analyses when we have dichotomous data or yes-no data. Instead of having numerical data where we can actually calculate means and medians and standard deviations and things like that, this is the technique we use whenever we have data that's just in categories. Yes, no, like, dislike, but also remember we can use this for data that has more than two categories as long as we form two categories from it. So we could have Republican, Democrat, Independent, Green Party, Tea Party, all those different affiliations, but then we could still use this type of analyses because we could just talk about the proportion of the population that is Democrat, right? Or the proportion of the population that is Republican. It doesn't have to be a strictly yes or no question anymore. That was only when we were dealing with binomial distributions. Now we can deal with multiple choices, so to speak. Okay, so first we're going to learn how to just estimate the population proportion. We're going to construct a confidence interval around that estimate to give us a better idea of what's happening in the population. And then later on we're going to figure out how big of a sample size we need to gather in order to get our confidence interval down to a certain size. You've all seen polling where they say, so and so has 53% of the vote plus or minus 2%. Well, that plus or minus 2% is the size of their confidence interval. In order to get that confidence interval down to that size of only plus or minus 2, you have to have a certain size to your sample. And so there's a very easy calculation to figure out that sample size. So if you want to be more accurate and say, you know what, on the 10 o'clock news channel, instead of saying plus or minus 2, we want to be able to say plus or minus 1. How big of a sample of voters do we need to go out and ask who they're going to vote for? And then you can figure that out and then go gather your sample and then be able to say plus or minus 1 instead of plus or minus 2. Okay, so we start off with a point estimate. And a point estimate is just a single number measurement of your sample that you use as a guidepost for what you think the measurement is in your population. Now in this lesson we're dealing with proportions, but this exact same idea of a point estimate can also be applied to the mean or the standard deviation or a few other measurements as well. But those are the three that we're really going to concentrate on in most statistics courses. So we're going to start with the proportion. Just like most times we have to look at some vocab, right? And we have to look at some syntax. So this little kind of upside down V on top of your P is called P hat. So whenever you hear someone refer to P hat, they're referring to P with that over it. And that's just the proportion of your sample. And then, of course, just P by itself is going to be the proportion of your population. It's kind of like how X bar, right, was the mean of your sample, and then mu was the mean of your population. We'll always have corresponding variables for the sample versus the population. Here's a simple example. We took a survey of 1,007 adults, found that 85% of them know what Twitter is. So the best point estimate of P, the actual population proportion, i.e. what proportion of the entire population who knows what Twitter is the result that we get from our sample. As long as our sample is fairly large and it's a simple random sample, so there aren't built-in biases and things like that, we can feel fairly confident that the results we get from our sample should be pretty close to the results we get from our population. Remember when we talked about our z-scores and things like that, we know that we have a sample distribution. And even if our population isn't normal, we know that if we sample over and over and over again, we're going to get a distribution that is normal in shape. And we know that the average of our samples, right, so the average of whatever we're calculating each time from our samples, that average will in fact be the population measurement that we're going for. So if we're talking about proportions, we take a proportion, we write it down, we take another sample proportion, write it down, do that over and over again. The average of all those proportions should actually be the true population proportion. Well, we only took one sample, and that one sample gave us a proportion of 85. Well, isn't it more likely, just by the laws of probability, that that sample is somewhere in this range rather than, way out here or way out here? It's not impossible for it to be out in the green zones, but it's unlikely. So that's why this becomes our best point estimate of the true population, because it's likely that it's in this area, so it's likely that it's close to the actual proportion that comes from our population. Now, our confidence interval, or sometimes called an interval estimate, is just a range that we build around our estimate. So our best guess, right, our best point estimate in this case is the p hat. And then we build some interval around it. We go plus and minus some amount. And that gives us a window where we're pretty darn sure that that window contains the actual proportion of the population. Maybe it's over here, maybe it's right here, maybe it's right here, but chances are it's somewhere in that interval, so we can be fairly confident that that interval contains the true proportion of our population. Our confidence level is just the probability that it's in that interval, and it's always going to be 1 minus alpha. Alpha is going to be our error rate, right? How much can be outside of our interval that we're not accounting for. So if we set alpha to be 0.05 or 5%, then our confidence interval is going to be 1 minus that, and then we're going to be 95% confident that the thing we're looking for is within our interval. So when you hear a 90% confidence interval, that just means alpha equals 10%. Now, interpreting a confidence interval is very important because a lot of people get this wrong. There's a right way and a wrong way, right? Let's say for our previous example with the Twitter thing, that when we built our confidence interval, we got 0.828 and 0.872 as our interval. So we were able to go plus and minus and build that interval. The right way to interpret this is to say we're because this was based on an alpha of 5%, so that's why we're 95% confident. So we would say we're 95% confident that the interval from 0.828 to 0.872, or roughly, right, 82.8% to 87.2%, does contain the true value of the population proportion. So we're 95% confident that the true population proportion is in between those two numbers. Now, this doesn't mean that 95% of the time the population proportion is in between those two numbers, because the population proportion doesn't change, right? So it can't be somewhere 95% of the time and then not be somewhere 5% of the time. It's a number and it doesn't change. The population proportion is set in stone. We just don't know what it is. By building this interval, we're just saying that we're 95% confident it's in between those two numbers. Basically, what we're doing is we're saying the size of this interval means that if this is my distribution of samples, and we know that this is the average of my samples, which is going to be the actual proportion of the population. Every time we pick a sample at random, we're going to get different p hats, right? We could get a p hat over here, we could get a p hat over here, we could get a p hat way down over here, we could luck out and get a p hat right near it, right? We could get all these different p hats. But if we go out 2 standard deviations in both directions, and I'll put this in blue, right? We go out 2 standard deviations in both directions. That area, as we saw before, is 95% of all of our data, right? These are our samples. So that means 95% of our samples will have a p hat that lands within that range. Okay? Well, now think about taking this range as an actual length, right? That has a length to it. And put that same distance around each of your p hats. Can you see that if you took this distance, and I'll put it in another color so you can see the difference, and put it around this one, let's say, you go out to about here and up to about here, and that would be your 95% confidence interval around that green p. And does it contain the red p? Yes, it does, right? And you can see very clearly that this one would also contain it, and hopefully you can visualize how this one would also contain it, because if you took this same length, this green piece, and just shifted it over and centered it on this, it would go from about, I don't know, about here to about there. You see how that would still contain the p? But, however, look what happens when we come out here to this one. If we build an interval around that one, it's going to go to about here and down to about there, right? It's going to be around that. And you see how that doesn't contain the red p. So 95% of the time, with an interval that big built around each of these p's, it's going to be big enough to contain the red p, but sometimes, 5% of the time, it won't be. That's why we're 95% confident that the interval we have is actually one of the green intervals and not this crappy gray one that doesn't contain it. So that's the way you want to interpret those. Is because of the way probability works, we know that 95% of our samples are going to be, they're going to have a p hat that's within a certain fixed distance from the actual true proportion of the population. So if we build an interval around that p hat that is the same size as that fixed distance, then we know that interval will contain the true proportion. And so 95% of the time, all of those intervals that we build around those p's will be wide enough to capture the red p, the red proportion, the true proportion of our population. But 5% of the time, those p hats are too far out. They're outside the blue zone. And so because they're outside the blue zone, when you build that interval around it, it's no longer wide enough to contain it. Because remember, this is symmetrical. So the right side of the blue zone is the same distance as the left side of the blue zone. So as long as your points are anywhere in this interval, the left side of this 2 size interval, let's say this is a distance of 4, just to make the math easy, right? So from here to here is 4. And so you're going to build an interval of 4 below and 4 above. Well, if you're anywhere within this interval, if you go 4 units to the left, isn't that going to immediately put you to the other side of the red line? And same thing if you're anywhere on the other side, do it in green. If you're anywhere in the green interval, you're within 2 units from P. So if you add 2 units to the right, you're going to be big enough to capture P. But as soon as you cross this line and go over to the left too far, your 2 unit interval, right, is no longer long enough to capture P. And that's what's happening. So make sure you can interpret your confidence intervals correctly. Oftentimes confidence intervals are used for hypothesis testing, and it's nice to understand how the two work together. And for now we might do it a couple times this way, but really the p-value method is the much better method for dealing with hypothesis testing. And that's what we're always going to do once we learn how to do hypothesis testing for real, is we'll always use the p-value method. So don't spend a lot of time trying to use confidence intervals for hypothesis testing. Just understand how the two correlate, but really we want to move on to the p-value method because that's the better, more commonly used way of testing hypotheses. Just like before, we have to deal with critical values. So when we talk about finding a critical value, we're finding that z cutoff score. Here's a good picture, right? If we're trying to be 95% confident, then we're going to have 5% outside of our confidence interval. And that's why you're going to see oftentimes it's written as z of alpha divided by 2. Because if you're 95% confident, then that means your error rate, your alpha rate, is 5%. And because you have to put half in each side, this area, right, is half of your 5%. That's why it's alpha divided by 2. So if we want to be 95% confident, which seems to be kind of the gold standard, you don't always have to be 95, but it seems to be what most people use. Then you're going to go plus and minus a certain amount that captures 95% of your data. If you look that up in tables or use technology, you find that it's plus and minus 1.96, right? It's really, really close to plus and minus 2. When we talked about that 68, 95, 99.7, we said those were approximations, right? We go approximately 2 standard deviations to get 95, and we see that it's 1.96. So the critical values that we're looking for, those z's of alpha divided by 2, is just that 1.96. It's the cutoff that says everything to the outside of that is considered bad, right? It's outside of our confidence level. And later on, that's what we're going to call our rejection region when we're talking about hypothesis testing. Here are some common critical values that you'll use over and over and over again. So it's probably a good idea to write them in your notes somewhere so you just don't have to keep looking them up or you don't have to keep using technology to figure them out. Now remember, these are critical values when we're doing a normal confidence interval or a two-tailed test. So it's only when you have 2 tails, right? Both sides are bad. So on the inside is your confidence level, and then the outside is half, right? Half of alpha. Margin of error. Your margin of error, which is normally denoted by a italicized or script E, capital E, is the biggest kind of space you can go above and below your estimate and still be within your level of confidence. So your margin of error is basically just half the width of your confidence interval, right? Because you always go plus and minus in both directions. So your margin of error is just half the width of your overall confidence interval. So if you want to look at this picture, this distance from here to here is E, and so is this. Right? Your margin of error is just the plus and minus that you put on your estimate that gives you your confidence interval. Now we're going to have different formulas for calculating margin of errors for every single thing we're going to do. We're going to start with proportions, we're going to move on to means, we're going to talk about standard deviations. They all have different formulas. You can memorize these, you can use these if you want to, but it's always better to just let technology do it for you. Because even if you let technology just give you the final answer, meaning they just give you the confidence interval, and let's say they go, all right, your p hat, but they don't, let's say you don't even know anything. You don't even know p hat. You just know that we're dealing with proportions, and you get a confidence interval that goes from, let's say, 80 to 86. And I'm just picking whole numbers to make the math easy. So that's my confidence interval. That's my low, that's my high. So that means I've got some interval that goes from 80 to 86, and it has to surround my p hat symmetrically, right? There has to be exactly half the distance on both sides. Well, what's the overall distance between these two numbers? And you can see very easily it's 6. But let's say the numbers weren't really easy. How can you do that mathematically? Well, isn't it just 86 minus 80, right? So it's just the upper bound minus the lower bound. And that gives you 2 times your E, right? That gives you the whole distance. So if you want E, don't you just divide that by 2? So you take the distance, which is 6, you cut it in half, and that tells you your E is 3. You went plus and minus 3 in both directions. You can also now find p hat, because p hat is just the average of those two numbers. Take 86 plus 80, divide by 2, and that will give you 83. Or, once you have E, you just know you can add it to 80 or subtract it from 86, and either way, you're going to find p hat. So all this stuff is strongly related. So what I'm trying to tell you is, if you use technology and it just spits out a confidence interval, but the quiz or the homework asks for E, well, you can still get E very easily from your confidence interval. Or if it asks for p hat, and you didn't know that already, you can also get it very easily from your confidence interval. It's all related. So some more symbols, right? We've seen these before. We know what n is, we know what p is, we know what p hat is, blah, 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 blah. Now, if we want to estimate our population proportion, there are certain things, right? Our sample always has to be that simple random sample. The conditions for the binomial distribution must be satisfied as far as we have to have a fixed number of trials. The trials need to be independent. There are 2 categories of outcomes, and the probabilities remain constant for each trial. Now remember, this is not a hard, fast rule. We don't need 2 categories. If we have multiple categories, we can always turn it into 2 categories by saying there's the category that we're testing for and everything else, right? So if we're trying to figure out what proportion of our population is independent, for voters, well, then they're either independent or they're not, even though there's multiple categories, and we just have a probability for being independent and a probability for not being independent. And then there are at least 5 successes and failures. Remember, successes means number of things in your sample that have the category you're looking for. So in this case, at least 5 of the people you randomly sampled need to be independent, and then at least 5 of them need to be not independent. So your sample size would have to be at least 10 at this point. That's just key to make sure that the math works, because if your samples get too small, you don't get a normal distribution, and if you don't have a normal distribution, the z-scores don't really apply, and then the proportions don't really apply, the probabilities aren't really right, and your confidence intervals really aren't accurate. So we're just making sure that we're living in a normally distributed world. Here is the confidence interval with all of the confusing gobbledygook. Right? Oh my gosh, the p, what does all this mean? Well, it just means that the true proportion that is in the population is somewhere in between, right? P hat minus E and p hat plus E. Well, what does this junk mean? Sorry, this junk. P hat minus E and P hat plus E, that's just your confidence interval. You calculate some P hat, you go up a distance of E, right? You go down the same distance of E, and that becomes your confidence interval. And so all we're saying is that P is somewhere in that confidence interval. We don't know where. It's not, doesn't have to be directly in the middle. It's just greater than the low end and less than the upper end. And then this is just restating the formula for finding E. Another way of saying this is if we write P hat plus and minus E, here is what it is, right? If you take your P hat and you subtract E from it, that gives you the lower end. Go back to our example where P hat was 83 and E was 3. Then 83 minus 3 gives you that low end of 80. 83 plus 3 gives you that upper end of 86, and there is our confidence interval that we saw from our previous example. Procedure for constructing it, pretty simple. And this is going to walk you through how to do it by hand, but why would you do it by hand when you can just use technology? In StatCrunch, it's very easy. Click on Stat, go down to Proportion Statistics, because we're dealing with proportions. One sample, because we only have one sample. With data, this is the option when you actually have raw data. So had you gone out and actually collected a bunch of data, and we're trying to count up number of successes versus number of failures and do all that, you would use this option. You would have to have all of your data in one of these columns here, and then you would have to tell it what a success was. And let's say you wanted a success to be yes. Here's where it gets tricky. It will count that yes different than that yes different than that yes. So you have to make sure that all of your data is case sensitive. And likewise, that, right, is different than that, is different than that. So it becomes a real pain when you're dealing with non-numeric data, right? When you're dealing with proportions, so we're dealing with non-numerical data, we're dealing with yeses and nos or categories and things like that. So again, if you had voters and Republican, Democrat, Independent, and you wanted Republican to be the success that you're looking for, you'd have to make sure that they were all written as rep and none of them were Republican, right? Or if you're looking for Green Party, they'd have to all be GP, or so you just have to be consistent. So that can be a big pain. So just be careful when you're doing it that way. For most of our examples, we're just going to be dealing with non-data, right? They're not going to give us the data, they're going to give us a summary. And this is a lot easier because now all we have to do is tell it, okay, there were 840 successes out of my entire sample of 1007. Do I want to do a hypothesis test or a confidence interval? Right now we want to do a confidence interval. We can change it to a 90% if we wanted to, or a 99 or whatever. We're going to leave it at 95. Don't worry at all about this method. It doesn't impact anything, and we're not going to deal with that. All you do is click compute. Here are your results. There are your successes. There's your N, right, your total. Here's your P hat, your sample proportion. Here is the lower limit and upper limit, so those two numbers make up your confidence interval, and this is your standard error. Now, don't confuse that with E. That's not E, that's your standard error. I know, it seems, isn't it the same thing? No, E is your margin of error, not your standard error. The standard error is pretty much the same thing as your standard deviation. And then because we're 95% confident, our E ends up being, remember, almost 2 standard deviations. So it's 1.96 times that. In fact, if we do the math here with our next example, you'll see how that works. Which brings me to our next example of doing it with the calculator. To do it in the calculator, press your stat button. So just like stat up here, we're doing stat down here, and then go over to tests. You're going to be doing a lot of things in the test menu, so get used to going to this menu. Everything that ends in the word test, those are going to be your hypothesis testings, and all the ones that end in interval, those are going to be your confidence intervals. And they're kind of in the same order. Z-test, T-test, two-sample Z-test. Well, as we scroll down, Z-interval, T-interval, two-sample Z-interval, then two-sample T-interval, and then finally one proportion Z-test, or sorry, Z-interval, and one proportion, or two proportion Z-interval. So the one we want is one proportion Z-interval, because we only have one sample. We're dealing with proportions, and so it's a Z-interval for proportions. Select that. I've already typed in the numbers, 847, 107, confidence interval of 95. Have it calculate. And there are the same numbers, right? Just rounded differently. There's the same p hat, there's the same n. It does not give you your standard error, and it does not give you your e. I think there probably is a way to get the calculator to do that for you, to display it. I'm not sure how to do it, but it's really easy, right? Because if we want to know our e, we just know it's the upper, 0.86369, minus the lower, 0.81853. And that's the width of our entire confidence interval. So all we have to do is cut that in half. And there is our margin of error. And you'll see that that is not the same as our standard error. Our margin of error is about twice as big. And that's because the standard error is that standard deviation that's being multiplied by 1.96, because that's the z-score we get for being 95% confident is 1.96. So if we divide this by 1.96, there's that number. Okay. Again, rounded differently because the numbers we used here were truncated, right? They were rounded. So this number is also going to be inaccurate after a certain point. Everything matches 1, 2, 3, 4, 5, 6 for 6 decimals, and then after that it's no good because we rounded up here to 5, which is also a good thing to keep in mind. I've told you guys before, don't round unless you have to, because now you get inaccurate answers. Okay, so that's how we do it in technology. That's the way you should always do it, because doing it by hand, well, is a pain. But it's nice to know these formulas, because then when we don't get all of the answers we need out of technology, we can get them by knowing, hey, it didn't give me my E, my margin of error, but I can do it very easily by doing the differences between the two and dividing by 2, and then there's my E. Okay, so it's good to know these formulas for getting the information you need, but for the most part, just let technology do everything for you. So you can run through this example if you want. I've put the actual work on the slides as if you were doing it by hand. I would do it by technology if I was you. In fact, run this example in technology and make sure you get the same answers. Here's how we interpret it, because there were a couple questions on this example other than just finding the results. It wanted us to answer a couple things. So it wanted us to find the margin of error, it wanted us to find the confidence interval, and then it wanted us to answer a couple questions. The first one is, based on your results, can you safely conclude that more than 75% of adults know what Twitter is? And then, assuming that you are a newspaper reporter, write a brief statement that describes everything. So we did the work. We got our confidence interval of 0.828 to 0.872. So can we be confident that more than 75% of adults know what Twitter is? Well, we can be 95% confident that more than 75% know, because 75% is below our entire interval, right? Our interval goes from 82.8% up to 87.2%. So we're 95% confident that the true proportion P is somewhere in between those two numbers. So we're 95% confident that more than 75% know what Twitter is, because these numbers are all greater than 75%. And here's how you would write it up. Right? We're 95% confident that 85% of the people know what Twitter is. You could say that our sample resulted in 85% of, or 85% of our sample knew what Twitter was, and based on those results, we can be 95% confident that between, what was it, roughly 83 and 87% of everybody, right? Somewhere between 83 and 87%. And that's what this whole should not differ by no more than 2.2 percentage points. That's what they're trying to say there. I think they're getting a little extra wordy. They don't have to be that robust with their words. You can just say, in theory, we're 95% confident that the true population proportion is somewhere between 83 and 87%. Whenever you get results reported to you, always consider some things. If they didn't do a simple random sample, such as if they used a voluntary response sample, i.e. surveys, which they almost always do, then their results are suspect. Right? Voluntary response samples are biased, so their results are going to be biased. The confidence level should always be provided. It's often 95%, but they don't always tell you. So unless they tell you, you also don't know how confident their results are. The sample size should always be provided. Again, it just tells you how strong their results really are. And keep in mind that the size of the population is not a factor. It doesn't matter how big of a population you're trying to measure. It's more about how you sampled and the size of your sample. Those are the two big things. So never think that these poll results are unreliable because the sample size is a very small proportion of the population. Like you're trying to figure out the proportion of all people in the United States who know what Twitter is, which is a lot of people, and you only have a sample size of 1,000, which is a very small proportion of the population. That's not how these things work. So you don't have to worry about small sample sizes relative to the population. Does not matter. What if we want to flip these things around and go, okay, how big does our sample have to be in order to get our confidence interval small, right, within a certain plus and minus? We don't want to be plus and minus 2.2% like we were in our previous example. Maybe we only be plus or minus 0.5%. Well, that's where we use our formula for E, the margin of error, right, the thing that we plus and minus, right, that ends up being the size of our confidence interval, and we algebraically solve for n, our sample size, and we get this lovely thing, which again you don't want to do by hand. You can let technology do it for you. If we know what the p hat is, then we can plug it into that formula. If we don't know what p hat is, i.e. we haven't actually gone out and taken a sample first, because usually they'll do a pilot study and they'll get an idea of what p hat is, but if you haven't done that, then you just set p hat to be 0.5, which makes q hat equal to 0.5, which makes their product equal to the 0.25 that you see in this formula. The only reason why you do that is setting p hat to 0.5 gives you the largest possible product of P and Q. If P is anything bigger than 0.5 or smaller than 0.5, the product of P and Q ends up being smaller than 0.25, and by making this number the biggest, because it's on top of the fraction, it ends up making this number the biggest it can be. And so you're kind of hedging your bets. You're saying that no matter what P is, no matter what p hat ends up being, if I set it to be 0.5, my sample size is going to be large enough to keep my margin of error within whatever range I want it to be. If the sample size is not a whole number, you always round up no matter what the decimal is. So even if it comes out to be 83.1, you would round up to 84. Here's a simple example. We want to be 95% confident, and we want to make sure that our error is no more than 3 percentage points. And we'll do it two ways, assuming that we use a 66% or a p equals 0.66 from a previous poll, and then the second one, we just assume we don't know what p hat is at all. So in our first example, there's our 66% for p hat. We figure out what q hat is. We're setting alpha to be 0.05, right? Because we're 95% confident. So our z is 1.96. That's that one of those critical values that we use over and over and over again. We want our margin of error to be 0.03 or less, right? We want to be within 3 points in both directions. Put all those numbers in, do the calculations. 957.8, we round up to 958. We'd have to go and find 958 people to sample. If we didn't know what p hat was, we assume it to be 0.5, which gives us that 0.25. And now you can see with all the other numbers the same, our sample went from 958 to 1068. See what I mean about it always making it bigger? And again, we round it up, even though our decimal would round down. In a mathematical world, we round up because we want to make sure it's big enough. The sample's big enough to get E to be smaller than that. We've talked about this informally, that if we're given a confidence interval and we want to find p hat, we can just average the two numbers. That's what it is, upper limit plus lower divided by 2. And if we need to find the margin of error, it's just the difference of the two numbers divided by 2. And that's it, guys.